Hello, Physics, Mahatma Gandhi Memorial College. Let us consider the last portion of the Unit 3, that is the astrophysics, in which there is a small portion which is given as the evolution of stars. So, in general, we make use of the word stellar evolution with reference to the birth and the death of stars. We can say the different stages of a star as the formation of the gas cloud, fragmentation, protostar, contraction, ignition, entry into main sequence, and the further steps. So let us say this is the concentration of hydrogen which is present in between the galactic space. It is found that the density is very, very less. It is nearly equal to 0.3 hydrogen atoms per cubic meter. But remember, when we say the hydrogen atom, it is not at rest, but it is in motion. But it is observed that the intergalactic space is filled with the hydrogen atom. So if you consider the accumulation of so many hydrogen atoms from a very long distance, or if you say the diameter is the order of a few light years to 100 times smaller, and if all these atoms begin to collapse, we don't know the exact reason, but if by chance, if that takes place, then the atoms will begin to move towards one another or closer to one another, and that results in the formation of more and more atoms. Because of the gravity, the atoms will come closer, the gravitational force, but at the same time, these atoms are experiencing a pressure outwards, and therefore we have two different forces, the gravitational force acting inwards and the pressure of the gases acting outwards. And it may so happen that the gravitational pull of the different atoms increase in the temperature, and the atoms may begin to fuse together, and it may reach a particular stage wherein the light may begin to come out of that particular region. Then that particular region is what is called the nebula, that is the birthplace of the star, and the star itself is called a protostar. But in this particular case, we have what is known as the hydrostatic equilibrium, in which the outward pressure will be equal to the inward gravitational force. And because of the increase in temperature or the fusion that is taking place, that may take continuously for a very long time, like 40 million years. And then, depending on the mass or the core, different things may take place. So, in general, we say if the core mass is less than 0.1 times the solar mass, where m sun refers to 2 into 10 to the power of 30 kg, then it may result in the accumulation or the envelope of hydrogen atoms The temperature is very less, therefore that may result in only the convection zone, and that may burst itself into the formation of the asteroids, comets, dust, or planets. Whereas if the mass is more, then it is possible that we have higher temperature, and because of that, the hydrogen may begin to burn, and we have the convection zone. In that particular case, we say the star has entered into the main sequence. When the star enters into the main sequence, we have both hydrogen and helium in the core, and that may continue for something like 4 billion years. And then at the end, depending on the way in which the core is having the different elements, it may end up in different ways. If the central core contains the helium 100% and hydrogen 0%, then the envelope is mainly hydrogen, and we have the convection zone outside. That may take something like 8 billion years. And the end of the main sequence lifetime of a star, no hydrogen is present in the core, therefore no fuel, therefore core begins to contract, and the internal changes affect the evolution, and the core temperature increases, and the hydrogen shell begins to burn with inert helium core. This is important. At the center, in the beginning it was only hydrogen, whereas now it is helium. And in this particular case, we have helium ash here, and we have the burning hydrogen outside. And at higher temperature of hydrogen, helium begins to burn, and that particular process may continue. When the helium core is burning, the core temperature may rise up to 100 million Kelvin, wherein the helium fuses into carbon and the core density increases, the luminosity increases, and the outer radius increases considerably. Here we have the central core, and here we have the burning hydrogen, and the burning hydrogen increases, and then the star is said to be a red giant. In the case of a red giant, outer layer is thrown out, the surface cools, and the star bloats. And mass of the core determines the fate of the star. In particular, it is found that if mass of the core is less than 1.4 times mass of the Sun, which is called the Chandrasekhar limit, then the white dwarf is formed. No fusion, no radiation, then it ends up with a black dwarf. In particular, this picture depicts the life cycle of the Sun. So this is the starting point, and now we have come up to this particular point. This is the present situation, wherein we have covered something like 4.5 billion years, and then it may turn up into a red giant, and finally with the white dwarf. And the Chandrasekhar limit is now accepted to be approximately 1.4 times mass of the Sun. Any white dwarf with less than this mass will stay a white dwarf forever, while a star that exceeds this mass is destined to end its life in that most violent of explosions, a supernova. So these are some of the terminologies that we use. Nova, it is the transient astronomical event that causes the sudden appearance of a bright, apparently new star. That is what is called nova. A supernova releases much more mass than a nova. The supernova destroys its host star, whereas a nova does not. A nova usually occurs in binary star systems when a white dwarf absorbs a lot of matter, whereas a supernova can be formed by either chemical imbalance or core implosion. And again, in supernova, there are two types, type 1 and type 2. Type 1, luminosity reaches peak value in a day or two and then falls off. It is very fast. In type 2 supernova, luminosity reaches peak value gradually and then it falls off. Next, if the initial mass is high, then this super red giant explosion takes place. If mass of the core is of the order of 2 to 10 solar mass, then the fusion continues. Helium converts itself into carbon, which converts into oxygen, and that into other elements, and finally it may end up with iron. So we have what is known as the onion-like layers of a massive evolved star. And then the explosion may take place, and the central core may contain only neutrons, and that is what is known as a neutron star, which is having very high density. And a dense neutron star spinning and releasing radio waves periodically is sometimes called a pulsar. If the mass of the core is greater than 15 times the mass of the sun, then again we have this particular thing that is going to take place. The central core may become iron. This is the onion-like structures that we have. And when this explodes, here we have the supernova, and the central core again experiences the gravitational contraction, and that may result in the formation of a black hole. And a black hole cannot be detected directly. There are indirect methods by means of which it can be detected. And in general, the expression for the black hole may be obtained by considering the simple equation of the expression for the kinetic energy and the gravitational potential energy. That is half mv square is equivalent to gmm by r, wherein we get the numerical value for this particular radius as something like 3 kilometers, and that is what is known as the Schwarzschild radius. This is the intense X-ray flares thought to be caused by a black hole, and that's the artistic pictorial representation. And this represents the complete picture of how exactly a stellar evolution takes place. This is the nebula, low and medium mass stars, including the sun. If the mass is more, then it is the other way. If the mass is less, then it turns itself into main sequence. Even in this case, it turns into main sequence, but the mass is more. Both of them are in the main sequence, and in this particular case, it converts it into a red giant, and then a planetary nebula, and finally it becomes a white dwarf. If the mass is more, then we have red supergiant, and then we have supernova. And if the mass that remains is high, then we have formation of the neutron star. And if the mass that remains is very, very high, then we have the formation